welcome back. In this video, we're going to take a look at a sample dummy model and focus on all of the different aspects of logging, exception handling, tracing that we just spoke about, and see how we can incorporate all of that into this dummy model and run this in large scale on a Google Kubernetes cluster, and then have a performance benchmark done on top of it using work, and then looking at the outputs of that performance by examining the logs on the Google Cloud console. So what we want to emphasize here on is not that these tools are great, which is obviously the case because there's a lot of work that's gone into it, but the techniques that we follow here are repeatable. It doesn't matter whether you use Google Cloud in the future or not. The techniques that we follow is going to be something that you will, again, find benefit from, even if you use a different platform, right? So with that said, let's go into what we're going to do. As with the previous week's lecture, we're going to start off by creating a Google Kubernetes cluster. So that cluster is going to be the vehicle for us to execute all of our workloads. And because the cluster takes 5 minutes to set up, let's go ahead and get one started right away. So I'm going to go into Kubernetes Engine on my cloud console, going into clusters. Yeah, so there's no cluster today that's running. So therefore I can go ahead and create. So there are two ways to create. One way that we showed in last week's lecture is to go create it by hand, rather using the UI. The other way that I'm going to show for this week's lecture is to use a command line. So for the command line, I'm going to use the Cloud Shell. So let's open that up, authorize the Cloud Shell request. Okay. So I've got a bunch of these commands already, available as useful reference, and it's part and parcel of the artifacts for this week's lectures. So let me bring that up here. So I'm going to create this GKE cluster. That GKE cluster is going to be called as demo log ML cluster. So I'm going to take this and execute this. Okay. So the cluster is being created and configured. Let's make sure that the UI shows the same as well. There we go. The cluster is being created. So while this comes up, let's now take a look at the code itself that we're going to work with. And as with last week's lecture, we're going to be using the same Workbench instance, the Compute Engine instance for our coding work as well. So let me fire that up, and then we can operate on that code. Okay, so I've clicked on start. Let's wait for it to come up. So there are a couple of things that we want to do in the meanwhile. So you can go ahead and enable the APIs that we're going to use for the services of Google, which pertains to monitoring, logging, and tracing. So that's the set of APIs Google G Cloud Services enable. Okay, so once you do that, then you can start using these services natively. So as before, I'm going to try to go into this machine using the SSH in browser. So let's just wait for a few more seconds for it to start up. Command line execution has continued. So by the way, the parameters here, I'm giving it the name of the cluster, the zone in which I want the cluster to be created, number of nodes, which is 3. I'm giving it something called as the workload pool. The workload pool is a way for me to segregate the nodes of this cluster in a security zone by itself. So we're going to take a look at this in more detail in the security, you know, part of the contents for this course, which is the next week's lectures. I'm going to also enable cloud logging for both system as well as workload related information and monitoring for the system. So those are all flags that are available out of the box for GKE environments. So that's what I'm using here in the command. Okay, let's take a look whether the instance is active. I think it just turned active. Yes. So logging into the SSH in browsers, I'm going to kick that off. Hopefully it logs in. What I found in practice is that the first one or two occurrences of this authorizing the SSH in browser ends up timing out, and usually the second or third attempt works fine. So if you also see that issue, you'll see that problem come up as retry or troubleshoot. Just click on retry and try it out again. As expected. Anyway. Okay, second time lucky. So within this, I've got the artifacts set up in a particular directory. Let's open up the file itself. The file is called as demo_log.py. So within this file, I've got a bunch of telemetry related imports. So we saw some samples of it in the theory part of the lectures. So I've got a tracer also set up. The tracer is based on the Cloud Trace span exporter, which is the Google Cloud Tracer. So by using this Google Cloud Tracer bindings or SDK, I will get automatic open telemetry trace information be logged into the Google Cloud Trace. So I'm going to get structured logging also enabled. And the service that I'm calling it as demo logs ML service. Logging formatter will always use this particular formatter, severity, message, and timestamp in a JSON. And the handler uses this formatter for everything, which was okay. So structured JSON, right? That's the best practice I was talking about. This is still fairly generic, by the way. So the specific information of what you log should also be ideally structured JSON. Okay, the actual fast app API is defined here. Oops. Okay. And then the model itself is basically just a dummy model. It takes the input features provided to it in the payload, and it just simulates compute by just sleeping for 100 milliseconds, and then provides a constant prediction. In your homework pipeline, you're going to have to obviously do all of this work on top of your iris model. So keep that in mind. The dummy model is just a placeholder, and therefore the input schema is also just a placeholder. So there are two states that I want to maintain as part of the app state. One state is called as is ready, and the other state is called as is alive. So remember the liveness and readiness. So I'm incorporating those best practices here. Is alive is basically a way to say that this app is ready. This app is live, and therefore requests can be sent to it. So that's basically the alive indicator. To start off with, the alive indicator is marked as true. When it's marked as false would be when the app itself crashes, obviously, or if the number of pods in this cluster is below a certain minimum threshold, and which point we mark it as false. Is ready, on the other hand, is meant for when the model is ready to serve. So the app is alive, but the model might not be ready to serve because it's still not loaded up into memory, or it's dependent on a database for logging and the database is not ready yet, or the connections have not been provided to it yet, etc., etc. So I'm going to start off the is ready with false. So what this means is when the readiness check happens, and these checks happen automatically by Google Cloud, then when the readiness checks happen at readiness check happens and it returns false, then Google Cloud will not entertain any requests to be sent to this model or to this app. So that's what the significance of this flag is. So in practice, you're going to consciously decide when you want to set it to false, when you want to set it to true, based on the functioning of the logic internally. So there is a special event called as startup event. So on the event of the startup event, which is basically the first time that the app is coming up, I go ahead and set the is ready state of the app as true. Normally what should happen here would be like the load of a model from the disk or the job.lib file, and that load of the model will take a finite amount of time. Like if it's a deep learning network, then obviously it's going to take minutes or if not more, and in which case you finish all that work and then declare yourself as ready, and because until that point you don't want to service workloads. Okay, so the liveness probe is a function that I've defined. It accepts a GET request on an endpoint called as live check. And this is part of the probe that the Google Cloud Monitoring is going to do for us automatically. So with this tag, which is basically hints, like pedantic hints, the liveness probe will now be the function that's responsible for ensuring that the app responds back with a, hey, I'm alive, or hey, I'm dead kind of a request. So if the app state is alive, then it returns status as alive, right? Which is what is expected by the probe, or it returns a 500 internal server error. That's liveness probe. Also note that the liveness probe is listening on the live check endpoint, which is only accepting GET request. So if you do a post request, then the response back would be the post method is not allowed. And that post method not allowed is an error. And because of that error, the probe will error out. If the probe errors out, the liveness check would have failed. Okay, so keep that in mind. Liveness check fails means the pod would be considered as faulty. And if the pod is considered faulty, Kubernetes Engine will restart the pod. So what ends up happening is, if you don't set up these probes correctly, you might end up having errors in the probe, and the errors will manifest as a frequent restart of the pod again and again and again. I'll show you examples from the iterations that I was doing earlier on how this manifests. Okay, readiness probe, on the other hand, is for ensuring that the model is ready to serve. So here again, all I'm doing is just checking the app state that it's ready. And if it's ready, I just say status is ready. Otherwise, 503 service unavailable. Again, it's a GET request on a ready_check endpoint with a tag as probe. If you remember the middleware discussion, I've incorporated that here. So basically, I'm just logging the latency, right? That's what the duration is about. And that latency is logged into the response header itself directly as process time milliseconds. And the response is returned back. Okay. I've also got an exception handler defined here. The exception handler always is going to have a standard JSON dump format. It's structured JSON, useful for us to do tracing, rather do searching. Trace is obtained from the trace functionality that I've enabled here. So one request can be traced all the way back to even the error reporting. That's the advantage. And then the JSON response is constructed and sent back as the final exception. Okay. Then comes the actual logic itself. So the extent of setup that you have to do for your machine learning code is much more than the actual machine learning code itself. That's the norm, by the way. That's almost always the case. Okay. What happens here under the predict function? So the predict is, the actual functional logic is actually fairly straightforward. Let me just highlight it here. Right? That's pretty much it, right? The dummy model gets invoked with the input data, and then latency is measured, etc., etc. But the logger information is anyway going to be, attached to every single prediction. That's what this logger is. You can obviously comment it out, because every single prediction, I don't want the raw data to be logged. So you can remove this line if you like. The tracer start span is basically saying this step is called as model inference. And under this model inference step, this trace is going to compute the prediction, right? That's what this tracer information is about. And then it catches all the exceptions within the try block and then logs all of those exceptions and then raises the corresponding exception as an HTTP exception. Okay, so this is my code, and this code is now ready to be deployed on Kubernetes. So as before, I've got my requirements file. The requirements file has a bunch of requirements. Because the dummy model is not using scikit-learn, I've removed all those requirements. Obviously, in your Iris model, you're going to include all of those. The only addition that I've done here is OpenTelemetry exporter GCP trace. So make sure you include that in your requirements file. And then the Docker file itself is almost exactly the same as what we saw from the previous lecture. I think 3.10 versus 3.11 is the difference, and Slim. So this should not really affect much. But let's use Slim and 3. What happens here? Okay. So those are fine. With that, with those files, we are now ready to build the Docker image. So I've got the Docker build command ready. Okay. That's this command here. So what this would do is assemble all the requirements, including that OpenTelemetry exporter GCP trace, and then, build the final image of a Docker. Yeah, you see the OpenTelemetry exporter GCP trace here. Okay. So it's nearly done. There we go. It's successfully built a new image. So let's go take a look at all the images now. Wow. Okay. I've been doing a fair bit of experimentation. Let's look at the most recent. There we go. 6 seconds ago. Demo log 207 MB latest tag. And the image ID is mentioned here. Okay. Good. So as with the previous week's instructions, we go tag the image. And once we tag the image in our artifact repository, then we go push the image so that it's available to the artifact repository. Once the push happens, then from that point on, GKE can pick it up. Okay, the push is successful. I'll show you the manifests. Okay, so unlike last week's, hands-on session where everything was deployed using the UI, this time around, I want to, show you how all of this can happen from the command line. So what we did just in the Cloud Shell here is to spin up the GKE cluster. So that command is run successfully. Number of nodes is 3, etc., etc. So the cluster is right here. It's mentioned here. Let's take a look at the workloads. There should be none. There we go. There are no workloads yet because we've not deployed anything yet. So to deploy, instead of deploying using the UI, I've created what's called as the manifest, deployment manifest. It's a YAML file. It's got a few interesting things. So let me walk you through it. First up, I'm just giving it the name of the service, demo log ML service. Minimum 2 replicas. Then it's got a service account that's attached to it. This service account is basically a special user which will allow the service to log information to the various, GCP-native tools like cloud logging, monitoring, cloud trace, error reporting, etc. So that system user that it uses to log all of this information is called telemetry access. So we'll talk about how we set it up. The containers are basically from the artifact registry. We're just calling it the fast API container, but you can also call it the ML service container or demo log ML service container. So that's fine. Then I'm pointing it to the artifact registry. The demo log latest is basically the image that we just created a few minutes ago. the port is 8200. I've also defined a readiness probe. The readiness probe checks against the ready_check endpoint, which is also port 8200. And the initial delay is 5 seconds, and then the period is 10 seconds, which means from the 5th second onwards, every 10 seconds, it's going to check whether the model is ready. Now, in practice, this is actually too frequent, but this is just to show you how these kinds of checks can really help with making sure that the health of the system is always maintained, or you're aware of it in the first place. Liveness probe is going to check against live_check. Here, its initial delay is 15 seconds and then 20 seconds of period. And then finally, the resources associated with it. The minimum resource for a request would be 100 M for CPU, 128 megabytes for memory. Likewise for, the limits are 500 and 512. So that's the deployment manifest. There are two other manifests I want to show. Service is basically the exposed web service for this entire, machine learning model. So the exposed web service is going to be called demo-log-ml service on TCP protocol, port number 80, but target port is 8200 within the container. And this will be using a load balancer type deployment, which is exactly what we did last week's lecture, but on the console. Then the last manifest here is what's called as the horizontal pod autoscaler manifest. So here, for this service, demo-log-ml service, I'm saying that the minimum replicas I need at any point in time is 2, but the maximum is going to be 10. And what's going to help me decide whether I scale up or not? It's CPU utilization of 60. If the average CPU utilization is 60, maintained for a period of time, then it's going to automatically spin up a replica. If for a replica or a pod, if the utilization is less than 60 for a period of time, then it'll shut it down. So that's what the autoscaler does. Great. So I've set up the cluster in my shell, and this cluster is called as demo-log ML cluster. But I need to be able to operate on that from my workbench instance so that I can deploy these manifests. So the way I can do that is by using the credentials. Let me first do the credentials part. Okay, so now I can start operating on that particular Kubernetes context. So before I go any further, there's a one-time setup that you'll have to do. First, you'll have to create in your G Cloud a telemetry access is a service account. I'm just going to do that here, but it'll return that I've already, created in the past. Yeah, already exists. Make sure that you use some shortcuts like this, so it's easy for you to not have to type everything again and again. So that's the project ID shortcut. So now just to show you, project ID maps exactly to the project ID that I have. So once you've created the service account in G Cloud, you can go map it to the appropriate project information, especially for logging. So that's already done. So I don't have to worry about doing it again. Same way for CloudTrace agent as well. So both of these are done. Now, every time you create a GKE cluster, you've got to additionally map the Google Cloud Service account with the Kubernetes Service account. So these are, nuances that we will take a look at, like some of it in the next week's security related discussion. But for now, suffice it to say that you've got to create a Kubernetes Service account, and that's going to be attached to this GKE cluster, the demo-log-ml cluster. And then you've got to do the mapping between the Google Cloud Service account and the Kubernetes Service account so that the two system users can talk to each other. Okay, so the mapping is called annotation. Okay. So I think it's denied because I'm already logged in and it's already set up for me. But when you execute, it should be working correctly. Okay. So with that setup, we are now able to map the service accounts to the cluster and have the service account, which is telemetry access, automatically be used by the Kubernetes cluster to log information to the various Google Cloud services that we will use. So just to show you, the deployment.yaml specifies the telemetry access as a service account name. And that's what we created just now. Okay. So now we are ready to deploy. Just to confirm that all of this works fine. So let me just show you that the annotation exists. There we go. The annotation exists and it's giving it to telemetry access, the Google Cloud Service account. So the Kubernetes Service account has the right annotation to the Google Cloud Service account. And the bindings are also fine at the IAM level. There we go. Default telemetry access. Yep. So it's got the right bindings to the workload identity. Okay. So it's time to deploy. Let's deploy one by one. Okay. So now the deployment has been created. So this will now bring up the Kubernetes workload. So let's go take a look at workloads. Refresh this. There we go. So the status does not have minimum availability because the pods have not become active yet. So let's leave it at that for now. Let's go back and deploy the other manifests that we have. Okay. So the service manifest has been deployed, which is the exposure of the web service, and the horizontal pod autoscaler has also been deployed. So now that all of this is deployed, let's go get the external IP address that is now going to be exposed by this Kubernetes cluster. It is still pending for access because that service is not set up yet. So let's just give it a bit of time. In the meanwhile, we can go back and take a look at what's the status of the deployment. Okay. The deployment is active. That's what the green indicates. The CPU memory or utilizations have all started to log some data. The horizontal pod autoscaler says it's unable to read all the matrices. It will fix itself in a minute. The replicas are 2. Both of them are ready. Both of them are available. Fantastic. You can take a look at the container logs separately if you like. The status is okay for the service. Okay, what else? Both the pods are running successfully. The exposure is not yet been configured as of that point in time. So let's go see whether the exposure is available now. Expose service is available. Super. There we go. That's the external IP and the port number is 80. So now we can pass a curl command against this and get a prediction. That's the hope at least. But before we do that, let's go back and take a look at the logs because it's fairly interesting on what's happening. So I'm going to go to container logs. Okay, it's I'm going to actually open it up in a different instance. Okay, so within the logs explorer, there is a specific arrow that you see here, which is called jump to now. The box right to the left, to the left of it is the time range. By default, it's got an hour granularity, and the time range tells you what portion of the data are you viewing at any point in time. You can pick the latest time range by either visually navigating here, the timeline, or the better approach that I've seen, which is very easy to do, is just to say jump to now. Jump to now will automatically pick up the latest 1 hour pertaining to what you're doing. So if you look at the most recent 1 hour, there has been a bunch of errors regular logs, etc. So I can quickly navigate to what I want to see by, either focusing on the severity. Let's say, for instance, I want to focus on error and see what exactly has happened. It's reverse ordered by time. So it's showing the last 1 hour in ascending order. So if you look at the current time, it's 1:14. So as of 1:11, the last time the error occurred was 3 minutes ago. And it was an error that just said UVCon is running successfully, which is the success message that we would get when the Docker is running successfully. So it's logged as error for some reason, which is something we will debug at a later point in time. But for now, the application startup is complete, which means it's ready to accept requests. Okay, so that's good. So let's get going. I don't want to focus on error anymore. Let's look at all of the logs. There are a variety of other useful things that you can do. So 84% of the results are similar, can be hidden. That's a very useful way to, remove information that's not contributing anything meaningful to you. Okay, so you can say hikes of the entries. Anyway, you can play around with this. Few things I want to point out. Now that the cluster is up and running, you can start seeing these ready checks and live checks. So these live checks happen frequently, live checks happen once in 15 seconds or 20 seconds, I think. That's what the deployment is. Ready checks happen once in 10 seconds. Ready checks, and there are 3 containers, right? Because there are 3 replicas. So each replica has a check that goes on to it. And everything is returned okay. So that's why these clusters are up and running and they're not getting shut down. If the live check or the ready check were to fail, then appropriate action gets taken by the Google Cloud automatically. So for instance, if the live check fails, and it fails, let's say, for a couple of times, then GCP will automatically, Google Kubernetes Engine, GKE, will automatically restart the pod. And that's a problem. Or if the ready check were to fail, then we wouldn't accept any request. But for now, both of these are not failing. That's why the health of the cluster is also shown as healthy. Sorry, where is the workload? Yeah, the workload says it's okay, and it's deployed onto 2 pods. Okay, fantastic. So we've got now everything that we need. Let's just plug in the port number information. Okay, we'll plug it into our curl command as well, and then have this be executed as the prediction. There we go. So it's predicted 42, confidence is 0.99, which is the dummy model output. Now, this is one specific request. How do we trace this? Let's go take a look. First up, let's go to the latest log information. Okay. And if you now see in the latest log information, there is a predict post that's happened and that returned okay, which is exactly what we would expect because we got an answer. But just before that, there is an error. But the error is just logging a severity of an info, which is basically a wrong mapping. So something in the code is not correct. That's why even the UVCon starting up and all, we're all logged as errors, but they're all actually, info messages. So you can correct it in your homework submission. But effectively what this logging is doing is logging the prediction, including the trace ID that is available to it. This trace ID is what allows us to trace logs back to the entire span, right? The input is given as 1.0, 2.0, which is what we saw. Prediction 42.99 is what we obtain in return. Latency of 100.32. Remember, 100 milliseconds is anyway going to be spent in time sleeping in the dummy model. So 100.32 is as optimal as it gets. So all of that is fine. Just to show you why this particular log step is having error and something that you should fix is this one here. If you see this logging information, this logger.info is the one that's, logging it with severity as error. So you can debug this and then change that appropriately so that it doesn't show up as error. Okay. What we were doing, we were looking at traces, right? So let me open up a new console just to show you how trace information looks. Trace Explorer. You can click on that. So far I've executed one request, and let's see what comes up. Great. So in the last 1 hour, there's only one request for model inference that happened at 117, which is the one that we took a look at. Notice that the duration of this is 100.718, whereas in the log, the latency is given as 100.32. And if you go back to the code, the latency that's logged here in the logging, that latency is from the time the dummy model start time is, right, till the time that the dummy model function executes. So it's got about 100.32 milliseconds, 100.771 milliseconds or 72 milliseconds. So about 0.42 milliseconds is the time it took extra for the entire trace to get logged. So that's what we should understand. And this trace is available to you as a specific ID. And in this case, there is only one service, which is the model inference service, which is run. Therefore, the trace is not very complex. It's very simple. This is one service, which is the model inference service, and all the time that's spent as being spent inside the model inference service. If you had multiple services or multiple handoffs, all of them will show up one by one. And that's the advantage of having tracing here. Okay, so we took a look at tracing. What else? Okay, next up, we're going to now, start doing a performance run. So for the performance run, we're going to install work. So the way I'm going to do that is by issuing this command. Okay, I don't need to do it right now because I've already installed it, but you should do it. Go to your Cloud Shell and execute sudo apt-get install work, and that will bring in the work package. And then for the work script itself, so there's a programming language called Lua. Don't pay attention to that too much, but effectively work expects its specification file to be Lua compatible. So I've just created this specification file, which has a very standard payload information, which is exactly what I gave in the curl command. It's a post request with JSON payload, which contains these input features. So with that, I've now created a payload information, and I'm going to, send it against this external URL. External URL is different now. That's 34.171.149.251:80. Right, 34.171.149. There we go. So now we are ready to run this command. There are multiple parts to this. Let's break it down one by one. Starting from the rightmost, of course, the prediction URL that I'm going to hit. Work is a mechanism for benchmarking against multiple concurrent requests. So the nature of the payload, I'm giving it as a script, which is a Lua script. We just saw that. I want it to document latency. So that's what the latency flag is about. Then I want to run the test for a 30-second duration. And in that 30-second duration, I'm going to run 100 concurrent requests across 4 different threads. So that's my performance benchmark. So let me run this. Work command is not found. Fantastic. So I think the installation doesn't get carried over from one shell to another. We know that already because shells are ephemeral. So let me install it again. Okay, that's done. So let me execute work now. Fantastic. Okay. Running 30-second test, 4 threads, 100 connections against this URL. Okay. Now it's time to start taking a look at the traces. Let's see what comes up here. Okay, superb. Whole bunch of new traces have come in. All these new traces are as a result of the executions that we are doing now. And as you can see, the time duration has started to vary because the concurrent workloads are all hitting the same pods. Okay, let's go take a look at the log explorer. Let's jump to the latest time. I'm still hiding the similar entries. Okay, now we start seeing a lot many more log information with the predictions, because these are all pertaining to the individual traces, individual benchmark requests that have come in. Fantastic. Okay, so this is how the performance benchmark has been logged. So now if you see, because there are multiple different requests executing against the same pods, the readiness check that happened in between when the test was executing failed. And the failure is because the context deadline has exceeded, because the timeout that I've given for the readiness check is lesser than the time that it took for it to respond. So therefore it failed. So this is a warning that the Google Cloud monitoring is giving to us. If it keeps happening again and again, then it will decide that it can no longer accept request. Like this probe, which probed this particular pod, and the pod that's shown here, F5 FCC, that pod will get marked for pause. No more requests will be sent to it. But the good part is we are running the test only for 30 seconds, so I don't believe this should be a problem. So the readiness check will come back to being okay again. Anyway, let's go back to where we're running the test from. Where are we running the test from? We're running it from the Cloud Console shell, right? Yes, there we go. Okay, so it ran, the average latency is 1.35 seconds. That's significant, given that the backend is actually executing is 100 millisecond. Standard deviation was 433. The max was 1.97, which is significant, I would say, because the standard deviation is 64%. Number of requests per second that it was able to process using this minimum pod configuration was 5.96, roughly about 6. Maximum was 30, which is not bad. Latency distribution, if you see, the 99th percentile is 1.97. 90th percentile is 1.86. So if you now want to optimize and say that, look, I want to process more and I want to get this average latency down, you can do one of two things. Obviously, you can improve the model. Like in the dummy model, I just put a sleep, right? In your actual model, you would do some model optimizations, like the quantization, etc. The other approach would be spin up more pods and keep it ready. So that's, warmed up models, right? So that could be the other thing. So it finally processed only 543 requests, whereas I'd asked it to process 100 requests, as many as it can, always 100 at a time for a duration of 30 seconds. So if each request took 1 second, then for 100 requests to get processed, let's say it would take 1 second each, right? If that happens, then I would be expected to process 100 times 30, which is 3000 seconds. If my throughput was actually 100 requests per second, but my throughput is not 100 requests per second, my throughput is 6 requests per second. Therefore, proportionately, the overall throughput for the 30-second window is lesser. So totally, I was able to do only 543 requests in this 30 seconds. Errors, how many errors were happening? There were about 512 errors that happened, mainly timeout related errors on the socket. Okay, so that's in a nutshell what happened with the specific performance benchmarks. So as homework, please do the iris pipeline with all the logging, exception handling, tracing, and latency monitoring, all of that that we showed you in this code, in this dummy code, put it all in your Iris code, get it up and running, show it working with the logs explorer and tracing using a simple curl command on one request. And once that's done, issue the performance benchmark on a much longer window, right? Let's say it's a 5-minute window. Issue it on a 5-minute window. 100 requests can be scaled down to 10 requests, or you can retain it at 100. Let's retain it at 100. Let's retain number of threads as 4, and then execute that. When you execute that, you will eventually get results based on this output of work. That should be part of your homework output. Additionally, also provide logs explorer outputs which show the either the readiness check and the live check fails because the pods are not able to handle the extra workloads, in which case they could be marked for shutdown. So you can show all of those. Or if those work successfully, you will also be able to see the horizontal autoscaler kick in. The horizontal autoscaler will then gradually bring up more pods to handle the extra workloads. So please show that output as well if that comes up as part of your execution. So thank you. Hopefully you got a very good sense of how monitoring, observability, and response work hand in hand. And you've also got a sense of how automation within GCP goes a long way towards making the life of the MLOps engineer easier. Thank you.